All right. Well, hi, everybody out there. Today, we're going to talk a little bit about multidimensional clustering in Apache Iceberg with Z-ordering. I know that's a lot of different technologies, but we're going to kind of walk through all of them. It's really mostly going to be a talk about the ideas behind this technology and why we care about multidimensional clustering in the first place. To start with, let's just talk a little bit about who I am, why you should care what I have to say about anything, which you probably shouldn't. But in case you're still tuned in, I used to be a big Apache Spark Cassandra person. I did a lot of work on the Apache Spark Cassandra connector that was done at DataStax when I used to work there. Now I work at Apple and I'm an Apache Iceberg contributor. So I spend a lot of time thinking about how to get Iceberg faster. And one of the things we've been thinking about a lot lately is adding Z-ordering to Apache Iceberg's suite of other capabilities. Now, there's a lot of reasons behind that, but the main goal here is that we want to improve file skipping performance inside of Apache Iceberg. Now, if you aren't familiar with Apache Iceberg, it's a data lake data table format, which basically lets you represent many files on disk as a relational data set that you can do transactions on and work on and all that. So why do we care about file skipping? Let's just break it down really simply. The really big problem in big data is that there's data and there's a lot of it. And the big problem here is that hard drives are slow and life is short. We have to store things, we have to read things all the time. And usually the best thing we can do to improve performance of any big data system is just read less data. So the thing we want to do almost all of the time when we're planning out big data systems is figure out how can we read as few files as possible to answer a given user query. So how do we think about this? Well, let's take, for example, a completely unpartitioned table filled with nice Parquet files. So here's a table I've got here. It's got 3 columns. One is job, one is X, one is Y. Pretty boring. Let's say that I've got just some random job that's writing data into this table. It's coming from some streaming source. So my Parquet files that I'm writing are more or less all kind of mixed up. Okay, so here's an example file I just wrote. Wrote a file, it has metrics in it. Now, little did you know, the metrics in each Parquet file tell you the min and max value of each of the columns in that file. So this is really useful for people who are trying to plan queries because you can tell right off the bat whether or not a certain file is going to be relevant to your query. But let's say that my job is writing data basically randomly. So every single iteration that writes a new file basically writes a new file with the exact same bounds because it's basically putting in randomly distributed data in the full range of possible values that it could be getting in a batch. So I end up with a bunch of files that from the metric perspective look exactly the same. Now, they might have different values for other columns or something like this, but in this example, I'm saying that each one has a min and max value that's exactly the same for every column. So this is really bad. And this is really bad because now whenever I want to do a query, I have to look at every single file that's in my table. So for example, let's say I just want to select where job is equal to 1 and X is equal to 20. Well, if I do that, I have to check every file which possibly would have X equal to 20. And that is every single one of these files. Okay, so I have not gained anything from these metrics. So what do we do next? Well, the next thing that most people do is we start adding partitioning. Now, if we have a logical grouping that always makes sense for our queries, we can then logically group up files. And it looks a little bit like this. So let's say that we're going to just partition our table on that job column. Because let's say job is just something that we always ask for data within a single job. We're never asking for data amongst many jobs. We're really just always looking at one job. Okay. We're doing a little bit better here. Let's say we write out all of our files now. Our writer now is going to be smart, and it's going to put all of the files with a single job value inside of the partition of that job value. Okay, so our data is organized a lot better now. So now when I do that same query, if I say I look for where job is equal to 1 and X is equal to 20, the very first thing I can do is a partition pruning. I can basically say there's only one partition that has any data files that could possibly match my query. So there we go. I've cut out 2/3 of the data just by doing this one little partitioning change. Now, the problem here is that X equals to 20 predicate that filter is not really helpful still, because every one of my files still spans the whole gamut of values that's possible for X. It goes from 0 to 100. So this isn't good, but can we make this better within this system? And the answer to that is yes, we can do that with sorting. Now, before we get into ordering and things like that, let's just talk about just a normal hierarchical sort. Let's say I just sort the data based on a column. Now, in particular, in this example, I'm going to take my data and I'm going to sort it on just the X column, okay? So sorting the data on the X column means that all the files I produced, I'm going to take and rewrite such that they have an exclusive set of X values. So one is 0 to 33, the next is 33 to 66, the last is 66 to 100, and ignore the fact that I missed the inclusive exclusive operator on those greater thans. You understand what I'm doing here. Now, when we do our same query, we're going to be a lot better off, okay? So we have all these partitions that have now have their data ordered inside of them. When we do a query, select where job equals 1 and X equals 20, now only a single file matches. Our first step of pruning out the partitions illuminates 2/3 of the things here. And then having that X predicate now is really beneficial when I look at my parquet file, because I know that that parquet file, only one parquet file, has the possibility of having an X value equal to 20. Now, the problem with this is that once I've done this sorting, you'll notice that the Y column basically has remained the same. This is given an example where we assume that for every X value, there's still a pretty wide and random distribution of Y values, which means that if I'm looking for a specific Y value, I now am in big trouble, because I don't actually get any benefit. Unless I include a predicate on X, there's no way I can get really any benefit from a predicate on Y. So our sorting is effective, but it's really just a kind of singular dimension thing. Or unless you have very specialized data where you know that you're always going to sort, or you're always going to restrict on a sorted column before another sorted column. So for example, if you sort by time, and then after that by customer, if you always query on time and customer, you'll be pretty good off. But if you ever want to do a query just on customer, then your sorting based on time is going to make everything really bad for you. Okay, so how do we kind of get past this problem? Well, the answer is we need to invoke a little bit of math. We need to sort a lot smarter than we're currently sorting. So that's where it enters space filling curves. So I don't want to go through the real math definitions of all of this because it's complicated and I don't know all the terminology well myself. But a good way to think about this is we basically are just trying to draw a line over our data. We want to formulaically draw a line over our data and then number each pieces of data as we go through that line. So let me just go exactly through what that looks like. Here we've got this nice set of data. We have X going from 1 to 4. We have Y going from 1 to 4. And then we're going to just draw a line over it. So here's the line I feel like drawing today. I'm going to just go from the top left corner, go all the way to the right, go down one, and I'm going to go all the way to the left. Just going to cover the entire domain of possible X and Y values. So go down to the left, down to and draw this nice little line. And then I number all of my things. I've now drawn a space filling curve over my domain of X and Y, and then numbered my data points. So for this particular curve, point number 1 is the far upper left. Point number 13 is the lower right. So this curve is really fun. You know, I enjoy drawing lines. It's a lot of fun to do. We get to like draw little doodles and be happy about it. But this line is not actually helpful for our querying case. So the main problem with this is that it's not a locality preserving curve, okay? The key thing we want here is something that's called locality preserving. What do I mean by that? What I mean is that I want this line to basically have a short distance between values that are close in two-dimensional space. Okay, so what does that mean? Let's take 2 points, for example, here. Let's say we're looking at the difference between X equal to 1, Y equal to 3, and X equal to 1, Y equal to 4. Okay, these two spaces are only one space away in two-dimensional space. But on my on my space filling curve that I've drawn here, which is not a Z-order curve, on the curve that I've drawn here, they're actually a full 6 squares apart from each other. So this is a pretty big difference. Not exactly what I was going for here. Okay, so how can we make this better? Why is this bad? This is bad because it doesn't preserve locality. If I then group this up into files, we're going to end up with files that keep data that's not really closely related in the same file. In fact, if we build 4 exactly spaced files here, so imagine each file can only hold 4 data points, we basically get 4 files that look like this. And we basically just reinvented hierarchical sorting. So this is like not a good curve to use because we end up with the exact same problem we had before. We've ended up sorting our data on one column and ignored all of the important information that's in the other column that might help us make data that's more closely clustered on both dimensions. So again, if we did our query here, we've actually in no way benefited as long as we're doing a query on X. We only benefit from queries on Y. Okay, so this is just an example of what one of these curves can look like, and basically the game we're going to be trying to play, which is we're basically trying to draw a line that goes very close in 2 dimensions while still going through every single data point in our domain. So enter Z order curves. So it's called Z order curve because it looks like a Z. We're basically going to draw these little Z's all through our data. This is a kind of recursive pattern, and the larger your domain is, the larger these Z's become. And this is very different than our previous line. You'll notice that this line actually preserves locality pretty well in a lot of cases. So now those 2 points that we looked at before, x equal to 1, 3, and y equal, x equal to 1, y equal to 3, and x equal to 1, y equal to 4 are now only separated by a single square. They would be number 1 and number 3. So imagine I take that same file setup again, and I make 4 files based on this line. Instead of 4 files that are spread out amongst one dimension of my data, I get 4 files that are clustered on both dimensions. So for example, I'm going to make a file that's where x is greater than 1, x is less than 2. I'm going to get one, I guess the best way to look at this, it's hard when I'm not in person and I can't point at these things very well, but you can imagine there's the upper left quadrant, there's the upper right quadrant, there's the lower left quadrant, and the lower right quadrant. And all of those basically get their own file now. So this is a lot better because now if I want to query on X or Y, I can actually be selective. So this is really cool because now if I do a query, for example, if I'm looking for X equals to 2, I have to check 2 files. And if I check these sorts of things. So basically on X or Y, we can be selective. We can cancel out files. We can skip files. There are other curves, for example, a Hilbert curve, which is another example of a space-filling, locality-preserving curve. Looks a little bit like this, but basically serving the same purpose. Basically, in all of these cases of space-filling curves, in terms of data search and helping performance of data lakes and things like that, we're basically looking for lines that go through our data and get multiple dimensions close together in a one-dimensional line. So this is another cool little algorithm. You'll notice it does the exact same thing on my trivial toy example. And just to show this in action, let's imagine that we're doing a query of where x equals 3. We only hit 2 of these files. Same thing if I look for just y, I only hit 2 of the files. I've basically made it so that instead of only being selective on one dimension, like a normal hierarchical sort would be, I'm selective now on both dimensions. And if I combine them both at the same time, if I have a where x equals something, y equals something, I still get the same benefit because it will still only be in a single file. Okay, so that's what these kind of look like on this very weird little trivial domain I made, where x goes from just 1 to 4 and y goes from 1 to 4. So this becomes more complicated when we extend that domain to allow more values. And here's just some pictures of what that looks like. But the key thing I want you to see in this photo is that when we have sorted our data this way, we get these locally collected pieces of the domain. So you can basically see in both of these graphs that there's a repeating pattern that happens over and over and captures like small quadrants of the space up into a localized zone. And that's really all we want here. We just want to make sure that our data looks all nice and clustered like this. Now, this actually extends out to multiple dimensions, but of course becomes more and more difficult the more dimensions you add. Now, obviously, I just made a fake little trivial example, and I showed basically how this can benefit a completely dense domain. But what if we don't have that kind of domain? Like, let's say that we have these two columns, but they don't actually have values for every combination of X and Y. So let's just take a little look at what might happen. So starting with, let's assume that we just don't know the right number of files to make here. Say that we have to just make 3 files instead. Things are going to end up actually look a little weird, but we still get benefits because of the curve. But there's something else that we can do here to actually make this work a little bit better, and that's we can actually use the z-values themselves when we're planning our queries. Now, for example, let's say that we take one of those 2 divisions that I have here. We know that each one of these files, now that we've created these 3 weird-looking files, has a min and max z-value. So they have a min and max x value, a min and max y value, and they also have a min and max z value, the highest curve value and the lowest curve value. If we can transform the filters in our query into z-value based filters, then we can also use that when we're querying our data. So this is really useful. So let's say, for example, that we're missing a few pieces of data in our files. So we're missing, in this particular example, whatever would fill in at x equals to 2, y equals to 2, and x equals to 1, y equals to 1. So we've got 2 holes here. We end up making 3 data files. And the x and y ranges are exactly the same as if those pieces of data had been there, because they just look at the min and max values in each one. But we have a big difference here. We have a big difference in this z column, because each of them has this separate range of z values. So let's start by just using a little query that looks like this. We're looking for x is less than x is greater than 2, less than 3. Y is greater than 1, y is less than 2. Now, if we look at this, there's only 2 files that could possibly match this without considering our z values. Our bottom 2 files are the only ones that have x values within that range and also have y values within that range. But we can do better if we also use our z values when we're planning. So how do we do that? So if we look at the box that is surrounded by x is less than 2, y is less than I'm really bad at saying inequalities today. X is greater than 2 and x is less than 3. Y is greater than 1, y is less than 2. We draw a little box in our data, and you'll notice within this box of values that we're actually looking for, we can check what the z values are. And we can see that the min z value within this box is 10, and the max z value within this box is 15. Now we've got more information to actually do our query planning with. If we know that the z value has to be between 10 and 15, well, now all of a sudden, what used to be 2 files that we have to check is now only 1 file. Now I've indicated here in highlighted in white that basically there's only 3 possible data points that match this z value constraint. So if we add that together, you'll see that if I'm looking for z between 10 and 15, I can't check the second file and I can't check the first file because we know there are no z values within that range there. So this basically lets us save a whole lot of time and skip an additional file. So ideally, what we want to be doing here is not only organizing our data based on this z-value curve, but also storing our z-value as another piece of file metric that we can use to query plan with. So that's basically our goal for our implementation inside of Iceberg. Now we have to ask the question, how do we actually compute these curves? How do we actually apply them to real world data? So this is where it becomes a little more complicated. So to generate a Hilbert curve, you have to do some matrix math. Luckily, there is a really nice paper out called Programming the Hilbert Curve, which was then translated by David Moten into a Java library. So you can actually see this and do the math that actually generates a Hilbert curve. But basically, in that case, you have to say how many bits wide your domain is, and it basically will draw a curve within the bit field. For Z curve, for a z-value curve, it's actually a much easier representation to draw this line. All you have to do is interleave the bit representations of your columns. Except there's a small caveat to that. It's not just the bit representations, because we know that modern computer types are a little more complicated than just being lexicographically ordered bytes. So for example, an integer starts with a sign byte, which all of a sudden means that all of your negative numbers end up being larger than all of your positive numbers. So what we really need is to be able to interleave the representation of the bytes as if they were a lexicographically ordered type. So I wrote a little description here, which I'll read again. We would like to interleave the bytes of lexicographically orderable representations which mirror the semantically orderable representations. So we want to make byte representations that are lexicographically ordered. We can compare them highest bit to lowest bit, but they have to have the same ordering as the original data type would have had. So this is a little bit more complicated, and this is where some of the tricky stuff comes in. So we also want to make sure that these representations end up being very dense over the space that we're drawing the curve. But I'll just go over some quick examples of how we can get these kind of transforms, at least at a very simple level. So the key thing to remember here is we don't really care about our mapping being one-to-one. The only important thing is that if we give two, for example, integers, we want the two integers that are, if those two integers are different where one is greater than the other, then the byte representations that we create must have the same relationship. If they don't, then we won't actually be able to build an accurate z-order. So for a lot of types, this is actually pretty straightforward. So for example, those signed integers I was talking about are actually sortable, except for that first sign byte. So in the case of an ordered representation, a signed integer, all you have to do is really flip that sign byte, and then all of a sudden your negatives come before your positives, and all of your data is correctly sorted. Now, you can do similar but slightly more complicated things to floats and to strings, except at strings we end up with another problem. Now, our strings can be any number of bytes long, and what we really want is to be able to compare the most important bytes with the most important bytes of another column. So with strings, basically one of the cheap ways to get around this is to just truncate them to a certain length and say you're only going to care about that certain depth. But in the future, what we'd really like to do for all of this, and this is something we're currently debating in the community about how we're going to implement these in the future, is how we can bound these functions so that they're actually representative of the data that they were clustering, so that we can hopefully get a nice representation that fits well with the data that actually got z-ordered. Now, how are we going to actually use this inside of Iceberg? So the current implementation that we've been doing and we've been prototyping with basically adds this into our rewrite data file command. So if you're familiar with Iceberg, one of the cool things Iceberg has is the ability to automatically sort your data and reorder and bin pack your data together to get more optimal performance in querying. So like I showed at the beginning, that hierarchical sort of thing is already an automatic feature that you can use inside of Iceberg. So we're basically going to take that same logic, which can hierarchically sort data, and instead write a sort expression based on our z-order curve, and then have the data sorted on that instead. So basically, we'll take the same, we take the same command, and then we put in a z-order function instead of a hierarchical sort expression, and then we get our data sorted. So I know this was a lot of talk about z-order curves, not a lot of talk about Iceberg, and I'd be glad to talk a lot about that in the Q&A. But there's a lot of work left to be done on this implementation and also the discussion of how we're getting it done. And I would be remiss if I didn't tell everyone that Apache Iceberg is an open source project and everyone is welcome to contribute. Check us out at https://icebergapache.org or on site our Slack. There is an Apache Iceberg Slack, which is available to anybody. The invite link is on our main page. And if anyone has questions about Iceberg or doing this kind of space filling curves, I'd be glad to take those questions.